Welcome to homework.
We are given sets of ordered pairs of positive integers, and we are asked to give a recursive definition of each of these sets, and then to use structural induction to prove that the recursive definition is correct. So in part A, we're given the set S is the set of all ordered pairs AB, such that A and B are positive integers. And we have that A plus B is even. So first let's find the point nearest the origin as the basis step. To do this, you may want to graph it. Otherwise, you can sort of just do it by thinking about possibilities. So notice that the smallest possible pair, which would have 1 and 1, we have 1 plus 1 is 2, which is even. So it follows that 1, 1 is an S. We can't get any closer to the origin than this. So this is our base case. And as part of our recursive definition, notice that we can add all the other points by adding a multiple of 2 to either coordinate or a multiple of 1 to both coordinates. So it follows that if AB lies in S, then we have that A plus 2B lies in S, and AB plus 2 lies in S, and A plus 1, B plus 1 lies in S. And this is our recursive definition. Now, we'll use structural induction to prove that this definition is correct. So the basis step, now, we want to prove that A plus B is even whenever AB lies in S. So first of all, for the basis case, we have that 1, 1 lies in S, and 1 plus 1 equals 2, of course, is even, so this checks out. Now for the inductive step, assume that AB is an S with AB even. A plus B is even. Then by our definition, we have that A plus 2B is an S. A plus 1B plus 1 is an S. And we have that AB plus 2 lies in S. We have that A plus 2 plus B is equal to A plus B plus 2, which is going to be even since A plus B is even. We have that A plus 1 plus B plus 1 is equal to A plus B plus 2, which of course is even since A plus B is even. And we have the sum of two even numbers is another even number. And finally, A plus B plus 2 is the same as A plus B plus 2, which is even. Again, since A plus B is even. So it follows that property is true for the recursive step. And so by the principle of structural induction, it follows that A plus B is going to be even if AB is an S. So we've proven our definition is correct. In part B, we're given that S is the set of all pairs AB such that A and B are positive integers, and A or B is odd. So to find a recursive definition, first let's find the point that's closest to the origin. This will be our base case. You can do this either by graphing or just by thinking about it. So consider the smallest possible point, 1, 1. We have that 1 is odd. And so it follows that 1, 1 lies in S. And we also have that 1, 2 lies in S. And we have that 2, 1 lies in S. And this is as close as we're going to get to the origin. So these 3 points are our base case. And we know that all the other points can be obtained by adding 2 to one of the coordinates or both, because then we preserve the oddness of the coordinate. So it follows that if AB lie in S, then we have that A plus 2B lies in S, and AB plus 2 lies in S. And we could technically add 2 to both, but this is really the same as adding 2 to one coordinate and then adding 2 to the other coordinate for the new pair. So this is a good enough definition. Now, we are asked to prove that A or B is odd if AB is an S. So for the base case, we've already shown that 1, 1 is an S, 1, 2 is an S, and 2, 1 is an S. And we have that 1 is odd. So it follows that the base case checks out. And now for the recursive step, assume that AB lies in S, and we have that A or B is odd. So we know by our recursive definition, this means that A plus 2B lies in S, and AB plus 2 lies in S. So if A is odd, then we have that A plus 2 is odd. And so the recursive step checks out in that way. Now, if B is odd, then it follows that not only is B odd, but B plus 2 is odd. So both pairs have a coordinate which is odd. This checks out. And so, by the principle of structural induction, it follows that if pair AB lies in S, then it follows that A or B is odd. So we've proven our definition correct. Finally, in part C, we're given the set S of all pairs AB such that A and B are positive integers, A plus B is odd, and 3 divides B. So, first, we want to find two points which are in the bottom two rows of points. So looking at the bottom two rows of points, we see that, okay, if you graph this yourself, you'll see 1, 6 is an option. So is 2, 3. So first of all, notice that 1 plus 6 is 7, which is odd, and we have that 3 divides 6. So it follows that 1, 6 is an S. It's kind of the smallest we can get in a way. And then we also have that 2 plus 3 equals 5, which is odd. And we have that again, 3 divides 3. This is the smallest we could pick for this. And so it follows that 2, 3 lies in S. This is our base case. And now for the recursive step, we have that if AB lies in S, then we notice that we can obtain all the other points by adding a multiple of 6 to the second coordinate or a multiple of 2 to the first coordinate. So it follows that A plus 2B is an S, and we have that AB plus 6 is an S. Notice that we couldn't just add 2 to the second coordinate because then it's not clear whether or not, in fact, it means that B will not be divisible by 3 if we just add 2. So we have to add 6. And so this is our recursive definition. And now we want to prove this definition using structural induction. So for the base case, well, as we've already shown, we have that 1, 6 and 2, 3 are an S. And we have that 1 plus 6 equals 7 is odd. 3 divides 6. And 2 plus 3 equals 5 is odd. And 3 divides 3. So the base case checks out. Now for the recursive step, let's assume that AB lies in S. Then by our definition, it follows that A plus 2B lies in S, and AB plus 6 lies in S. So we have that again, A plus 2 plus B, this is equal to A plus B plus 2, which is odd. And we also have that 3 divides B, since that's what we were given. We have that A plus B plus 6 is equal to A plus B plus 6, which is also odd. And we have that 3 divides 6, so 3 divides b plus 6, since it divides b also. And this is all because a plus b is odd. And of course, if you add an even number to an odd number, you still get an odd number. So it follows that the recursive step is valid, and so by the principle of structural induction, it follows that if AB lies in S, then A plus B is odd, and we have that 3 divides B.